Hey guys, so like I mentioned yesterday, I'm not going to be in class today, but we still have some stuff to get through. So I figured I would just post this video of me going over this concept because there's no math involved. We're just talking about magnets, which I'm sure most of you have held a magnet, even if it was just a refrigerator magnet, in your hand before. And you have an idea of kind of what they do. So we're just going to talk about them in some detail and why they work the way that they do. So, first and foremost, when we're talking about magnetism, we're talking about an attractive or repulsive force that some materials have. It's a property of that material. And just like our electrical force, which can be attractive when we have opposite charges, or repulsive when we have same type of charges, this also is attractive and repulsive. Now, if a material has magnetism, has this property of being able to exert this force on things, we call it a magnet. Now, this is an example of a horseshoe magnet, which you might have seen in Looney Tunes cartoons, but it doesn't have to be in this shape. There are lots of different types of magnets, but all of them are able to exert this force over a distance. Now, even though it's really, really similar to our electrical force and our electrical fields, they're not the same thing, and we don't use the same vocabulary for the different pieces, but they are very, very related, as you'll see later on. So here we have a bar magnet, and you can see the different poles on it. So all magnetic objects exert a force between these two things, and it can be attractive or repulsive. So just like our electrical force, opposites attract, so south is attracted to north, and likes repel. So south it repels other south poles, and north repels other north poles. So let's think about some of the other forces that we've talked about. We've mentioned electrical force and how similar they are to each other. They're both attractive or repulsive depending on what you're putting up next to each other. But we also have forces like gravity. So we've talked about gravity before, and we have our equations for how to calculate it. Gravity is an attractive force, but it's never repulsive. So we've got forces that act similarly and forces that are similar but a little different. But something that magnetic force uh, and gravity have in common is that as you get farther and farther apart, the force decreases. It gets smaller and smaller and smaller. So just like how we're so far away from the sun that we're not immediately pulled to it, we orbit it safely. If you take two magnets, like if you take a south pole and a north pole and put them close together, you'll feel the force pulling them towards each other. But if you hold them really far apart, you're not going to feel that force as much because, again, as they get farther apart, that force decreases. So that's something that magnetic force and gravity have in common that magnetic force does not have in common with electrical force. Electrical force is the same regardless of where you are in the field, so long as you are in the electric field. Now, the place where your force is strongest, your magnetic force is strongest, is at these poles. That is where it's strongest, and you'll see why when we go over what the field actually looks like. And we call these poles north and south. This is also where we get our names for our north and south pole on the Earth. Now, magnetic force is also different from electrical force in that you cannot isolate your poles. What I mean by that is I can't cut this in half and get a piece that is completely north and a piece that is completely south. So unlike our electrical force where I could separate protons and electrons, I could have a section that is completely electrons and a section that's completely protons and it would be fine. Magnetic poles cannot be separated like this. It doesn't work. If I take a bar magnet like this and I were to cut it in half, I would get two smaller bar magnets, both with their own south and north poles. So you can't separate them like you can your charges. Now, part of the reason is because of the magnetic field itself. this is kind of what it looks like here. We're actually drawing the field lines so you can see them, even though this is, again, it's an invisible force that acts at a distance. So your magnetic force comes from your magnetic field. So your field lines come out of your North Pole and circle back around to go into your South Pole. That's why it's strongest at the North and South Poles, because that's where your field lines are going in and out. Now, this, like our electric field, allows us to apply a force over a distance. So you can apply a force on an object without touching it. And how strong this field is, baseline, is based on the material that is magnetic. So some materials make better magnets than others. For example, iron is one of our most common magnetic materials. It makes really good magnets. But if you were to add a little bit of neodymium, which is another element, you can find it in the rare earths section of the periodic table, which is going to be the top row of the lanthanides and actinides. So if you look at my cabinets, where I have that section of the periodic table cut off, that top row is your lanthanides, and neodymium is number 60 in D. It's one of the rare earths. We call it rare not because it is actually rare, but because all the rare earth metals are really, really hard to separate from each other, which makes them expensive. So neodymium magnets tend to be expensive. But if you add just a little bit of neodymium to a regular iron magnet, it makes a much, much stronger magnet. So again, how strong your magnetic field is depends on the material that is exerting that magnetic field. Now, note, your field direction is always north to south. So just like we were talking about our voltage difference in our circuits, how it always travels from negative to positive, for your magnetic field, it's always north to south. Your field lines will always come out of the North Pole and go into the South Pole. Now, this is kind of what we see when we see that opposites attract and likes repel. So see here, opposites attract, we have a north pole of one magnet up to the south pole of a different magnet. You can see the field lines are coming out of the North Pole and going into the South Pole. So they pull closer and closer to each other. But we see over here, likes repel. So the South Pole, we have all the field lines are trying to go into the South Pole. So you have them rubbing against each other, going in opposite directions. And that makes it to where they push away. They don't want to be next to each other because they're getting in each other's way. Same thing with the North Pole. It's a little easier to see because your field lines are coming out of the North Pole. Here they're literally pushing on each other. So they're pushing each other away because they're getting in each other's way. So opposites attract and likes repel. And we can see that because of the shape of the field lines themselves. Now, Earth actually has its own magnetic field. Again, that's why we call these our north and south poles. When you have a compass like this, it's actually pointing towards magnetic north, which is slightly different from geographical north, not by a lot, but it's slightly different. And magnetic north moves sometimes, but not quickly, not often, and it's not enough, especially if you live, anywhere closer-ish to the equator. The closer you are to the equator, the less this matters. But our core, Earth's core, is made out of a lot of metals. And those metals are spinning in the core. Now, spinning metal acts kind of like a bar magnet and gives Earth its magnetic field. Now, this is super important because it's one of the things that protects us from the sun's radioactive particles that it shoots out at us. This magnetic field, because those particles are charged, forces them away from us. Now, notice here I have the field lines coming out of our South Pole and going into our North Pole. But I just told you on this previous slide that we always come out of North and into South. So funny thing, we have defined our North and South Pole backwards. So this would technically be magnetic South, and this is magnetic north. But we always call this the North Pole, and we print it to where compasses will point north. It's just a funny thing. It's not super important for navigational purposes because our poles flip every so often. Because magnets do that. The poles flip, and we can actually see in lava records how often this happens, how long it takes, because when lava is liquid, all the different magnetic materials such as iron that are melted in it can just kind of spin and turn until they're facing to align with magnetic north and south. But as soon as the lava cools, then they're stuck in whatever position they were in just beforehand. So if you look at lava flows, Hawaii is a great place to look for these because active volcanoes. If you look in the lava flows, you can see what direction all the different magnetic particles are pointing in, and that'll tell you which pole was magnetic north or south at the given time when that flow happened. And so we can actually see how often they flip and how long it takes for them to flip, which is pretty cool. All right, so all atoms can be magnetic. All of them, even if they're in a material that's not typically magnetic. The reason being is because they're charged particles. Like we have our positive protons, we have our negative electrons, and as we'll go over here in a minute, electricity and magnetism are heavily related to each other. So all of them have the potential to be magnetic. The difference between a material that is magnetic and a material that isn't is alignment. So in our magnetic elements, all of your atoms have aligned with each other. So all of their magnetic fields are pointing in the same direction. This allows us to add all of their fields together, and they make a field that's strong enough for you to feel. But in our non-magnetic materials, all of our atoms are not, their magnetic fields are not pointing in the same direction. And so you can't add their forces together, and they don't create a magnetic field that's strong enough for you to actually feel it and do something about it. So here's our difference between magnetic elements and non-magnetic elements. Now, ferromagnetism. So this is where you can make something magnetic by putting it in a very strong magnetic field. So if you are one of those people who are lucky enough to have like a magnetic drill bit or a magnetic hammer, the ones that'll hold the nails so that you don't have to hold it with your fingers and possibly smash and break your fingers, they can actually induce a magnetic field on the metal if they're held there long enough. So you can turn a material that is not magnetic but could be into one that is by putting it into a strong magnetic field. That field will force all of their atoms to align and make it to where all of their magnetic fields will align, and they'll have a magnetic field that's actually strong enough for you to feel. So you can make non-magnetic elements into magnets by doing this. And this is why your non-magnetic elements, iron, cobalt, and nickel, will stick to magnets, even though they themselves are not magnetic. Which is pretty cool. And iron, cobalt, and nickel are the only ones you can really do this with. Easily, anyway. So, like I said, electricity and magnetism are very, very interconnected. That's why we go over them in the same unit. So, a moving electric charge, so if you have charge and it's moving, that's current, makes a magnetic field. This is how they're connected to each other. So, if you've got a current flowing through a wire, it creates a magnetic field that is going circular around the current, around the wire. That magnetic field is going counterclockwise in circles around the direction your current is moving in. It can be a little tricky to visualize. Now, the stronger your current is, the stronger the magnetic field that it's going to make. So, the more current you have, the stronger the field. Now, you can use this property to make electromagnets. So, this is something that's only magnetic so long as it has the current going through it. So, this right here, this circuit right here, doesn't have any current flowing because the switch isn't flipped. So, notice it's not magnetic, it's not attracting any of the paper clips. But if you flip the switch and close the circuit so that the current can flow, now it is going to attract all your paper clips. So electromagnets are temporary because as soon as you turn off the switch, as soon as you stop your current from flowing, this isn't magnetic anymore. But so long as the current is flowing, it is. And once again, we see here switch open, no current, no magnet. Switch closed, current flows. Now we have magnet. Now, there are a couple of different ways that you can make stronger electromagnets. You can either put more loops of wire around your object. So the more loops you have, the stronger your magnet will be. So we have more loops on this one than we do over here. So we pick up more stuff, stronger magnet. You can also make a stronger current. So the stronger your current is, the stronger your electromagnet will be. Even though these have the same number of loops, we have an extra battery. So extra battery, more current, stronger electromagnet. And we use electromagnets everywhere. They're super important. So you can use electromagnets in electric motors. This converts our electrical energy into mechanical energy. So we change our electricity into the turning of the tires. And we also can use it in generators. So this uses an electromagnet to convert mechanical energy, the engine turning, into electrical energy. A lot of people have these in case they ever lose power in their home. Like I've got some relatives who live in Panama City, and whenever a hurricane comes through, they always got to make certain that they have their generators and enough gasoline to run them. So you're turning that mechanical energy that used to be chemical potential energy, because gasoline, they're turning that mechanical energy into the electrical energy using an electromagnet. And that's it for this section. So now that you finished the video, by all means, if you need to go back, pause different sections to make certain you get all of your notes filled out, do what you need to do. But I've also posted 2 assignments, practice page 23 and practice page 24 to Google Classroom. They should have posted the same time this video did. So take some time to do those in class. They shouldn't be too hard. And again, there's no math in this section. So I'm confident you guys can totally handle this. But if you have any problems or questions, please email me. I don't guarantee that I'll be able to answer emails tomorrow, but if I know that there's an issue, then when I come in on Monday, we can address problems as we can.